Welcome back, everyone. We are very excited to have Chris Bowman from the University of Kent as our second speaker today, telling us, and our second speaker overall, in fact, telling us about the tautological p-Kazhdan-Lusztig theory for cyclotomic Hecke algebras. As before, we'll take a little 5-minute break around halfway through. So please, if you have any questions, type them in and I will read them or wait until the break task. Please take it away, Chris.
Okay, cool. Thank you very much, Nicole. Can you guys see my slides right now?
Yes.
Oh, okay, cool. Okay, thanks. Okie dokie. So what I'm talking about today is joint work with Amit Hazi, who's here, Anton Cox from City, and my student Dimitri Mihalidis. Okay. So, okay, there we go. Right. So the story begins with Cheval duality. Okay. So I'm going to let GLH be the group of H by H invertible matrices, and I'll just start with complex and then I'll quickly change away from that. And I'm going to let Sn denote the symmetric group on n letters. And then Cheval duality is the relationship between these two things, which says that, okay, GLH acts on its natural module, right? Fine. So it acts on the nth fold tensor product diagonally, okay? Then because you've got n things, these n copies of the natural module, the symmetric group can act on the other side by permuting these n copies. Now, what Cheval duality says, amongst other things, is that this representation, this bimodule tensor space, decomposes as a direct sum of simple modules, or simple bimodules, where on one side you're seeing a representation for GLH indexed by this partition lambda, and on the other side you're seeing a simple or spect module over C for the symmetric group, again indexed by lambda. And then what is this indexing set which we've summed here in the background? Well, this is the one thing that I really added this slide in order to say, which is that this is the set lambda of all partitions of n, which I actually haven't written here, into H, at most H non-zero parts. So the GLH bit is saying, okay, well, you're only allowed H rows, and the symmetric group bit is saying, okay, and when you add up those rows, it must be n. Okay. And then the representation theory of the symmetric groups and the general linear groups is just then great. They're the same. You pass from one to the other through Cheval duality. And if we let, H and R vary here, so GLH, okay, H and N vary. Okay, I've used slightly conflicting notation. If I let H and N vary, I'll see all representations of symmetric groups and all representations of general linear groups eventually. And the reason I did this over the complex numbers was so that I could then say, aha, the same thing holds in characteristic P, except that I've replaced this direct sum with a sort of, oh, it's got a filtration kind of thing. So now tensor space has the same filtration by these partitions of partitions lambda into at most H non-zero parts of n. Okay. The important thing is that these modules are no longer simple. And so the big question, the big representation theory question for this picture is, well, if they're not simple, what do they look like? And so if you don't, if you're not a fan of anything on this slide, all you need to know is that I did this whole thing so that I could excuse restricting to partitions of n into at most H non-zero parts. And that this is a natural thing to do because of the way the symmetric group and general linear group interact. Okay, so this is a big question and we've been looking at it for a long time. So we've come up with a lot of ways of thinking about it. And the way that we're going to think about it today is something that I'm going to call categorical Cheval duality. And so on one side of this picture, I'm going to have what I call the graded representation theory of the symmetric group. which is what Raphael was just talking about at the beginning of his talk. So there it was called the KLR algebra, or the quiver Hecke algebra. There's different names for it, but I'm just going to think of it as a nice graded presentation of the symmetric group, and sort of try to forget about the fact that there's a big isomorphism theorem going on there. And what I'm going to say is, okay, we've got this lovely graded representation theory of Sn that we want to understand. And in order to do this, people have gone on a really long walk through a lot of different things, through geometry and categorification and parity sheaves, and lots of stuff has come to play. And the point of this talk is going to be that all that long and sort of increasingly complicated machinery that you go into the further and further from what you thought you were doing, all that sort of technical and deep theory, you can actually bring it all back. And the idea was that it was all living there in the symmetric group to begin with. So it's not so foreign as perhaps it might seem. Okay, so I said that the right-hand side of this picture I was thinking of as graded Sn. So the symmetric group, what is it? It's permutations. And this grading of Sn means that, okay, if I want to look at Sn in characteristic P, then I need to use P different colors on the strands in the permutation. So here I've got orange, green, blue, yellow, and pink. Orange, green, blue, yellow, and pink. So this is characteristic P is 5, and it's the symmetric group of size 9. N is 9, the characteristic of the field is 5. On the left-hand side, I've got some crazy thing that I've never seen before, something new and exciting that's been going on for 10 years now. And it's something weird, and we want to understand the left-hand side in terms of the right-hand side. And the right-hand side is already, like, it's got a lot going on. It's already got this grading. There's already some sort of categorification thing going on in the background, but it feels like home, doesn't it? It looks like a permutation, so it's not so scary. So we've seen what the diagrams look like at the top, and now we're going to talk about the generators. So on the right-hand side, the generators, well, you just need an identity thing and a transposition thing, and you need it for each color. So here I've put Z over PZ as these 5 colors. So this little cycle here going around is the fact that P is, well, 5 here. I put a ... so P can be bigger than 5. So all you need to do is draw all the transpositions, but using these different colors. So there's more generators now for the symmetric group because you've colored them. But the coloring, so this is really important, the coloring on the right-hand side is coming from the prime. Now, on the left, we've also colored in these pictures, but now the coloring is coming from some sort of Lie theory thing, right? So I put simple roots. So if we think of the left-hand side as coming from GLH, then there are H minus 1 simple roots. So H minus 1 simple colors on the left-hand side, H minus 1 colors rather. And on the right-hand side, there are P colors, P for the prime. Okay. And then there are relations. And my point here was simply that, okay, on the right-hand side, example relations, well, it's not the symmetric group. It is something graded and new and exciting. But it looks a bit like the symmetric group, doesn't it? We've got something that looks like the braid relation here, except that there's an error term. And the error term in this case comes from the fact that if I look at orange and blue in my little pretty circle just above, orange and blue are next to each other in this coloring. Okay, so now we've seen a relation for the KLR algebra, the quiver-Hecke algebra, or just fancy symmetric group. And on the left-hand side, we've got different looking relations which seem more exotic. They don't feel like the braid, but maybe they're not so crazy after all. And then, so the theorem we're going to talk about today is that these two worlds are isomorphic. And obviously, I'll make that a bit more concrete. So that's why there's a giant isomorphism sign. And some of the consequences of this isomorphism are, well, if the algebra on the left is sort of, its decomposition numbers are essentially, by definition, the p-Kazhdan-Lusztig polynomials. So you can define p-Kazhdan-Lusztig polynomials in two ways, I think. I don't know, there might be more. One is geometric and the other is categorical. And I'm going to stick with this sort of categorical definition that it comes from this diagrammatic Zergel bimodule thing on the left. And so if we can prove that these things are isomorphic, then, well, then we've shown that, oh, okay, well, if we're going to define the decomposition numbers on the left to be p-Kazhdan-Lusztig polynomials, well, then, of course, the decomposition numbers on the right are p-Kazhdan-Lusztig polynomials because they're isomorphic. And that's the sort of tautological in the title. And there was one more thing I wanted to point out here. Oh, so the word I haven't used here, so this is just an aside, maybe for people who aren't familiar with this whole setup. This Zergel bimodule world is sometimes called the diagrammatic Hecke category. And so you might be like, oh, why are you telling us that the Hecke category is isomorphic to the Hecke algebra? That seems like a non-theorem. But the point is that there are always two Hecke things turning up in any Lie theory question. So on the right is we want to understand the decomposition numbers of a non-semi-simple algebra, Sn, and its Hecke algebra, as n varies over all possible ranks. Sorry, did I say the left? I meant the right. That was the picture on the right. On the left, what we've done, so this is a categorification of the semi-simple Hecke algebra of level of rank H. So that's where its non-semi-simplicity is coming from. And so people have always known that a semi-simple Hecke algebra controls the representation theory of the symmetric group. And this is what's going on. I don't think I explained that well. And so you should probably just forget that I said that. It was better before. Okay, so I'm now going to talk about the combinatorics that allows us to move from one side of this picture to the other. So I need a Euclidean space, which I'm going to denote by EH. And this space is going to be, okay, well, I need H directions in which to walk, epsilon1 up to epsilon H. I'm going to look at what they span, but I'm going to modulo out by the sum being 0. So what this allows me to do is that I want to do H is 3 for this talk. So rather than me having to draw cubes in R3 on the left-hand side, I'm allowed to just draw triangles in R2, which is much easier to picture. And so that's why they're all at 60 degrees there. And you can sort of see that this is because you're just projecting three-dimensional space down onto two-dimensional space. And look at this fella here on the left. This is PHN, which we recall from the first slide. So I want to think of partitions of n into at most h parts as being embedded into this Euclidean space. And I've probably screwed up columns and rows at various points. Oh, no, this is actually fine at this point. I'm going to use the transpose embedding because we made a decision a long time ago that we've begun to regret. But it's just a convention. It doesn't matter if you use rows or columns. So this is how we think of partitions as being in a space. And we do this for a bunch of reasons coming from Lie theory. And one of them is that we can now understand the orbits of under this H affine Weyl group, this H thing on the left, as giving us the blocks of the symmetric groups as n's allowed to vary arbitrarily, but just for the 3-column case. So here's an example. So what I've drawn here is a finite amount of tiling because I only have a finite amount of space. But the things to notice are, okay, so H is 3. So I've done my 3 directions, but projected down onto 2-dimensional space. P is 6. So notice that all of these black lines are 6 pink lines apart. Okay, and n is 23, so I'm going to embed some partitions of 23 into here. using this map. And in fact, I don't the whole, this is why when people say, okay, I'm interested in anti-spherical Cazhdan-Lusztig polynomials, what they mean is they want to forget all of that space. And why am I forgetting all that space? Well, I've got this little arrow compass thing at the top right, which says that epsilon1 is to go north west, epsilon2 is to go east, and epsilon3 is to go southwest. And so if I'm a partition, then my first column is bigger than my second column, is bigger than my third column. So I never need, this space is, all of these guys are compositions, these aren't partitions. But when I restrict, I'm only interested in partitions, so I restrict to this space. Okay, and so here are a bunch of partitions of n is 23, and we're about to zoom in and have a little look at them. Okay, so we've zoomed in, great. And this is the same picture as before, and there are my dots that I said would appear. Okay. And let's say how these partitions appear. So I put the furthest away one is 2 squared, 1 to the 19. So question, can you guys see my mouse when I wiggle it around so that I can sort of,
Yeah.
You can, okay, great.
Yes.
So 2 squared, 1 to the 19. Okay, so 1, 2. So that's the partition 2. 1, 2. That's the partition 2 squared. Okay, and now I go 19 steps in this direction, like so, and then I reach that partition. So that's why it's 2 squared, 1 to the 19, partitions into a space, nice and easy. And here's another one, 3 to the 6, 2 squared, 1. So 3 to the 6, I go around in a circle, 1, 2, 3, 1, 2, 3, 6 times like this. Okay, and then I go 2 squared, 1, and then I'm at that point. So that's why that's that partition. And then here are all the others. You've got the point, I guess. I got the idea, I guess. Okay, so here we are embedding representations, labeling representations of the symmetric group for n arbitrary, but only 3 columns in this projection of 3-dimensional space. So we can put the labels of representations into the space. What about the actual bases of these representations? So if the points tell us labels of representations, then I'm going to tell you that the bases of representations are given by walks to that point. And of course, you already know that the spect modules for the symmetric group have bases given by tableau. And so that's why I've drawn this partition here on the right. I'm going to do a tableau on the right and a path on the left. And so here's this partition lambda, which is 3 cubed, 2 squared, lots of 1s. And I've colored this partition with the same colors that I used on the right-hand side in the earlier picture. So I've got orange, blue, pink, yellow, gray. Oh, I think the prime is 6 here. So orange, blue, pink, yellow, green, gray, green. And then I repeat. So those are the 5 colors, are the 5 elements of my field. Orange, blue, pink, yellow, green, gray, green, orange, blue, pink, yellow, gray, green, like that. It just goes on like that. So we've colored the diagonals of this partition with the prime 6 of my field. I know that 6 isn't prime, but I'd already drawn the picture on the left, so I was too lazy to update it. So now let's look at how this gives us a path. So I'm going to take steps in the first and second columns for a little bit. So I just go in directions 1 and 2 for a bit. Okay, now I'm going to add lots of things in the first column. So I'm just going to do a quick blast all the way up to there. And then I'm going to take a step in a different direction. And then I'm going to take a few steps down to here. So that is how this tableau on the right-hand side can be thought of as a path. Every time I add something in the first column, I take a direction in epsilon 1. Every time I add something in the second column, I take a direction in epsilon 2 and epsilon 3, etc. Okay, so this is how we think of bases of the representations of the symmetric groups as being embedded in this space. And there's a nice action of this affine Wahl group. So this is what we've recorded in these black thick lines. So what happens if I reflect my path in one of these black thick lines? So I'm going back and forth here to show this idea. And notice that what happens is that the colors match up. So if I reflect this first path here, which went 21, 22, 23, I've got this reflection here that it's touching. I'm just going to reflect through that wall, and the colors get preserved and the diagonals all match up nicely, and I can do it again. And so in fact, what you're seeing here is these nice reflections give you homomorphisms between these different modules given by mapping tableau or paths to each other. And all the colors match up nicely. And that's the point, because the prime is the field, the prime tells us the colors, and then the colors are just telling us how to move boxes around, which just ultimately tells us how to reflect things through this geometry. And this guy here is the a tableau that people are very familiar with in symmetric group world, which is the tableau where you just put things in the most dominant position. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, blah, blah. So I just needed to fix that bit of notation. So blocks of symmetric groups, as you allow n to vary, and you just consider a certain quotient, they're given by the points in this space, and moving between them, the bases are given by paths in this space, and then the homomorphisms and the decomposition numbers and all this is somehow given by reflecting these paths around this space. So what I've told you so far is bases of this algebra, and now I want to tell you about the algebra itself. So let's take two paths which terminate at the same point. So I'm going to have p is 5 now, because that's a much better prime than 6. And here's a step path which goes 1, 2, 1, 2, 1, 2, 3, 3, 3. And here's another path which goes 1, 2, 3, 1, 2, 3, 1, 2, 3. And both of them start at the origin and end at the point 3 cubed. So let's picture them. Okay, so same picture. So we've got these triangles in Euclidean space. This goes off to infinity here, whereas it stops there. So, but notice it goes 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then it goes back to the start. And the other one, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's just going around in a little circle at the origin. So we've now seen, okay, these are two bases of the spect module 3 cubed. Okay, fine. So we understand bases of the spect modules. But we can also think of the elements of the quiver-Hecke algebra, of the KLR algebra, of the symmetric group as just, okay, I'm going to write the path 1, 2, 1, 2, 1, 2, 3, 3, 3 on the top. 1, 2, 3, 1, 2, 3, 1, 2, 3 at the bottom. And then I join up the dots. So in the sort of ungraded symmetric group level, this is a bit sort of vacuous. It's sort of like, yeah, sure, you can move things around, you can do steps in different directions, and if you permute things, permuting things always gives you the symmetric group, fine. But notice that these colors actually match up. So both tableau here start with an orange 1, then a green 2. Then, okay, this third one here, 3 at the top, ooh, yeah, 3 at the top, goes to this point here, 4 there, and so that's got a blue strand, and then it just carries on like that. So this is just, so I don't think I explained that. One more time. So 1, 2, 1 goes to 1, 2 goes to 2. And this is the minimal path that preserves the labels on top of bottom. So okay, here I've got an epsilon 1, here I've got an epsilon 1, so I have to match them up. Here I've got an epsilon 2, here I've got an epsilon 2, match them up. So it's minimal in the sense that I haven't put any extra crossings in. It's step preserving in that every epsilon 1 at the top goes to an epsilon 1 at the bottom. Same for epsilon 2, same for epsilon 3. And so this is the stupidest element you could possibly associate to these two paths, isn't it? You're not going to add extra crossings, that's silly. And oh, the colors match up, well, that's nifty. So it's really just this is the obvious thing to do. And then the point is that you can think of this quiver-Hecke algebra as being given by these morphisms, these bijections between paths. Okay, and we've seen, I guess that you probably have this funny little symbol thing in the way as well, but okay, what that says, maybe that symbol will disappear in a moment, maybe not. Ah, there we go. So we've seen the algebra is given by morphisms between paths. The representations of this algebra are given by the paths themselves in some sense. Okay, so, righto. So what is the story so far? We're now just going to review what we've just been saying. We're interested in general linear groups and symmetric groups. The general linear group has this H, the symmetric group has an N. And the modules, spect lambda transpose and delta lambda, are recorded as points in a Euclidean space. And there's a sort of action of this affine Weyl group of type H, well, the symmetric group on H minus, well, the symmetric group on H letters, affine SH, quotiented out by the finite Weyl group. Okay, and so that was why when I let H be 3, I first tiled all of R3. Okay, I went, well, it was really R2, wasn't it? But then I took 1/6 of R2, that sort of top triangle, because there are six elements in the finite group SH. And this splits our algebra into blocks via these orbits and reflecting through these points through these reflections. And it also gives us bases of the representations of the symmetric group on n letters via these paths in this space. And one thing I didn't put as a bullet point here was that we also seen that there are morphisms. The actual elements of the algebra, the symmetric groups, group algebra, are just morphisms between these paths. Okay, well, that's all fine and dandy, but what do we actually want to do? So our aim, we're going to let the prime be bigger than H. Okay, that's standard in people wanting to understand the general linear groups. We always let P be bigger than H. And because of this Schur-Weyl duality setup, this seems natural that we should therefore let P be bigger than the number of columns in our partition. For each such partition, we have a simple module, and it's just given by taking that nice spect module with all those nice bases and quotienting that by some radical bilinear form. Form was long ago by Gordon James. I don't know what paper. And we want to understand, okay, well, if this gives us all the simples, which it does for this quotient, we want to understand the passage between spect modules and simple modules. And this is the decomposition matrix that Raphael was talking about. And then one of the big conjectures, well, two of the biggest conjectures for a very long time were that these should be things and this conjecture was not true, but it was important, and we're going to sort of talk about that a bit. So I guess it's probably halfway through, so I should probably take a break now. I'll just leave you with that is what we'll be doing after the break. Okay.
All right, great. Thanks, Chris.
I can't see you, so I'm very nervous that that you guys have disappeared.
I'm here. Sorry, I stopped my video in between. Yeah, thank you for the talk so far. If anyone has any questions, please, of course, step in and ask questions. Otherwise, everyone but Chris may leave for 5 minutes. So, Chris, can you actually? I don't know if it was just my internet or everybody else's. Do you mind? So the last like 3 sentences you said before you took a break, the part about James's conjecture, can you just say that again?
Oh, I don't think I was saying anything deep. Let's see. Can you see? Is it back to full screen now?
Yes.
Okay, I can see you guys. Okay, so I was just saying that what I've put here is the sort of old school stuff. So this is James, this is bilinear forms, this is sort of the things that you see from the symmetric group world. And 2 of the big conjectures when we were just thinking in terms of this symmetric group world, well, and Hecke algebras, obviously, given what I'm about to say, but when we were living in this old world, some of the things that people thought was that we should be able to calculate these decomposition numbers, providing P is bigger than H, or P is, yeah, bigger than H will do for Lustig. And the next step is going to be about, okay, that's not true. Let's see what we can do and what happens, and some things like that, I guess.
Thanks, Chris. Sorry, I wasn't sure if it was my internet or yours that you just completely.
Yeah, my internet said that it was shaky, so I was like, uh-oh.
All right. Shall we start? Are you ready? Excellent. All right. So welcome everybody back, and let's continue with the second part of the talk. Thanks, Chris.
Okay, so the first part of the talk was mostly sort of, oh, there's a little bit of titillating Zirkel stuff at the start, but it was mostly just, here is the symmetric group thought of in a slightly different way to how you normally think of it. And so now we're going to talk about the Zirkel sort of side of things and how we can think of it entirely within the symmetric group world. So, p-Kazhdan-Lusztig theory. So the aforementioned conjectures that we just mentioned are not true. So Riche-Williamson found counterexamples to these, and he did this in this setting called Zirkel bimodules, which is the fancy version that we're going to try and understand today. And the point is that just this setting is much more efficient for computation. So the examples you have to go to in order to find these counterexamples, they're huge ranks. And you'd never be able to sort of cook this up, you would think, within the symmetric group itself. I mean, we had 20, 30 years to try and do it just in the symmetric group world, and no one ever did. So clearly this is a much better way of doing stuff, because you can prove stuff that people thought was, okay, disprove stuff that people really thought was true and had no way of making these calculations. And this sort of combinatorics, which was called intersection forms of, it's computing intersection cohomology via these certain intersection forms. Calculating these things is now called p-Kazhdan-Lusztig theory. And the purpose of this talk is to show that all the p-Kazhdan-Lusztig theory in type A and this Zergel bimodule theory was somehow already in the symmetric group, and you can cook it all up in terms of tableau combinatorics after the fact. And where does this huge efficiency come from? This sort of, why are we able to make these much better calculations in the Zergel world? Well, it's the easiest thing you could think of to make a calculation simpler. It's just an idempotent truncation. And so the intersection form, which Geordie used to calculate these counterexamples to Lustig's conjecture, is just James's bilinear form on the spect module, truncated with an idempotent. So it's a bilinear form we had in the 80s, but we didn't look at it well enough. And this generalizes to cyclotomic Hecke algebras as well. So it's not just the symmetric groups. You can also do this for complex reflection groups, the infinite families, cyclic groups, Riche symmetric groups. And there was a conjecture here by Plaza and Libedinsky, and you can verify the conjecture this way. So back to my picture from earlier. We've now looked at the right-hand side in a lot of detail. Oh, okay, well, that was it. Okay, and we're now going to look at the left-hand side. So that was just a reminder of what we saw earlier. Okay, so step one. Well, I said there was an idempotent truncation, so we're not going to see the whole basis. We're going to see some Zergel tableau, let's say. So we can get, so what we're going to do is we're not going to look at all points. We've picked what's called the principal block. That comes from GLH rather than from the symmetric group, but we've taken this point here at the very start and we've reflected it. And so we're only going to consider paths which terminate at one of these reflections of the empty partition. And we're going to restrict further than that. We're not just going to truncate to a block, because that wouldn't do. That wouldn't be enough to get our result, because, well, we've always had blocks. They're nothing new. But the point is that we're going to restrict to a special family of paths, and we're not going to use, we're going to use the bare minimum of paths. And how do we do this? Well, we're going to use just 2h plus 1 different paths, where h, remember, here is 3 because I've got pink, green, and blue in my Zergel world as my colors. So I've drawn one of these paths, which is the one that goes through pink. Here it is as a tableau on the right, and as just a path on the left. So I said 2h plus 1. So for each color, I'm going to have 2 paths. So here is the one that goes through the wall, and here is the one that goes up to the wall and then changes its mind and comes back. And notice that these are related by the reflection through that pink hyperplane. Okay, so I've done it for pink. I need to do it for green and blue now, right? So here's the blue one. And this is a composition, remember, because we've left the dominant alcove, but we still need it. And here's the one where we reflect back to where we started. Okay, and finally, here's the one where we've gone through the green hyperplane, and here's the one we've gone back to where we started. So that's 2h paths, but we need one more, and what is it? It's the path that just goes back to the identity. And this is something that you sort of obviously need from the symmetric group world, because you need partitions of n, and so you need to be able to just do nothing. I kind of think of this as coming from the fact that, okay, I guess Zergel stuff comes from SLH minus 1, SLH, and the symmetric group is more, it's in Cherval duality with GLH, more is a better way of thinking of it. So for GLH, you need a determinant, and what is a determinant? It's just doing, well, we're using transposition, so it's just the sort of one row partition that you just add. So there's 2h plus 1 different paths, and that's enough to get to any path, right? To get to any point. And what have I done here? I've contextualized. So here, this green path, which goes through there, it's not actually the green path I started with, it's the reflection through the pink hyperplane of that path, which went like that. Okay, but using just these, okay, I've only used 3 paths here, not all 7. And I'm going to let path plus denote the things that can be obtained doing this. Oh, there we go. I've just used the little determinant path I told you about. And not just those, but the ones that can be obtained by reflection as well. So here, that was a path. and that's its reflection. And notice that, okay, I go up like this. And then here, this is this pink reflecty path, which goes up to the thing and back again. And then it just carries on doing what it did before. So interested in. So that combinatorics in place, I'm now ready to match up the idempotents in these two algebras. Are there any questions about the paths? Did that make sense, the picture? Cool. Okay, so let's construct an idempotent in both the Zirkel world and the KLR world using these tableaux. Okay, so here's my path, and I've colored it using the, for the tableau, I've colored it using this P is 5 combinatorics, orange, pink, orange, gray, pink, gray. Anyway, those 5 colors. And so here, it's an idempotent. What looks the most idempotent? Not doing anything. So this is the identity of the symmetric group, but then hit with this sort of coloring idempotent to make it see the characteristic. This is the an idempotent in the KLR algebra on the right. So, and where have the colors come from? Well, the path goes orange, green, pink, orange, orange, green, blue, orange, pink, blue, gray, green, orange. And so that's the sequence of colors at the bottom. But on the Zirkel side, I just record this with one color, the pink one, because that's the hyperplane I walked through. Now let's walk through another hyperplane, okay? Well, I've added a gray step in direction 10. Well, in this 10th step was gray, the 11th step was blue, and the 12th step was pink. So I've gone gray, blue, pink on the right, but I've just gone through one hyperplane on the left. So I just draw a green line. I just carry on like this. So each time I do some steps, obviously it takes a lot more work to do in the KLR algebra, but that's what we were saying. Zirkel is much more compact and easier to calculate with. We don't have to look at symmetric group on 24 letters. We can just draw 4 strands, which is much easier. Okay, so there's how we match up the idempotents. This is an idempotent in the Zirkel world because it's just sort of colors going down. And on the other side, it's the symmetric group on 24 letters. Okay, so here's this statement that I said that we wanted to do. So what I'm going to do is I'm going to define idempotents in both algebras, which I've already done. And here I'm just going to sum over all the tableau from the previous section. And ET is this guy on the right here, and 1T is this guy on the left here. And so that's why F is in the KLR algebra, little f, and capital F is in the Zirkel algebra. And then what the theorem says, this categorical Scherval duality, is okay, take the symmetric group and quotient out by the bit that you're never going to see because we're looking in Scherval duality. We're looking at just the bit that appears in h-fold, n-fold tensor space of h. So I've just quotiented it out by the bit that has to go. This annihilator here was never going to appear up. So just take the quotient of the symmetric group you see in tensor space, hit it on both sides with this f, this little f. Okay, well then there's some Zirkel thing that looks quite complicated, but you can sort of see the Kazhdan-Lusztig polynomials coming from this ah minus 1 affine quotiented out by the finite one. And all we've done is taken the Zirkel thing, which has a big bit of notation, but think of it as Zirkel thing, and then hit it with the corresponding idempotent on both sides. And they're isomorphic. How simple is that? So the H columns subquotient of the KLR algebra corresponds to the truncation of the diagrammatic Bott-Samelson endomorphism category. And therefore, H column decomposition numbers of the principal block, because I picked a block, of the symmetric group are equal to p-Kazhdan-Lusztig polynomials for p bigger than h. And that's the sort of tautology. And this slide has a lot of words on it, but we're going to draw the pictures now, and maybe things will become more clear as to how this isomorphism works. Cool. So I've told you the idempotent generators. I've said there is an isomorphism.
Chris.
Well, let's see. Oh, hello.
Sorry. Can I, there's a question, and Lars, so Torge asks, what is the direct sum over on the right-hand side?
Oh, I will refer to a meet. It's the direct sum of some Bott-Samelson things, but I don't know. Maybe I shouldn't have put it there. Maybe that's a Amit, do you know what that direct sum is?
So the direct sum on the right-hand side of the second line, Torga?
Mhm.
Yes, okay, so that's, yeah, that's going to be a, yeah, it's going to be a finite, it's going to be a finite direct sum over objects, and the indexing set is going to be dependent on n in such a way that as n gets bigger and bigger, you gradually cover all the elements inside your affine file group, your a hat h minus 1.
Okay, sorry. I thought it was this first direct sum, not the second one. Yeah, the latter one.
The first.
Yeah, I thought it was this one, but I guess it makes more sense that it's the latter one. That's a better question. Yeah, as Amit said, this is just the so each partition that you see, as the partitions get more and more, you go further and further into this alcove geometry, and it's just which alcoves labels do you see, as Amit said. Cool. So non-idempotent generators. So let's take two paths. And let's assume that they both terminate at the same point and they only differ by reflecting them around this geometry. Let's say they just terminate at the same point. Okay, so here is one such path. So it goes through pink, green, blue, green, and then does a little wiggle at the end. And it ends at that point, well, whatever that point is. But there's two walks to get there. So we need to be able to get from one to the other. We need to pass, what does the KLR algebra do? It passes between paths. So we need to be able to get from this path to the other path. How do we do that? Well, we just swap it. Oh, okay, well, not quite yet. So, oh, did I? Okay, so far it's green, blue, green, right? And so what I've done here is got you ready for what's gonna happen, which is that I'm gonna swap to blue, green, blue. So here, there's a, ignore the picture at the bottom for the now. Just look at, there's a path, it's going around, and the color sequence has changed from green, blue, green to blue, green, blue. And so what I've written here is boring, 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 all stays the same. Boring, 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 all stays the same. But now here, this is the path at the top, which goes through the blue bit first, then the green bit, then the blue bit. On the bottom, I've drawn the path which goes through the blue bit first, then the green bit, then the blue bit. So these are two different paths in this little bit, and that's where all the juice is. And that's why this is a bit that I haven't filled in yet. And so on the left-hand side, the Zirkel people just match stuff up. And on the right-hand side, we KLR people just match stuff up. So again, it's just the, okay, here's this generator for the Zirkel algebra on the left. And on the right, it's just, okay, notice that the top and the bottom of this Zirkel diagram tell you this path on the right as well. It's blue, green, blue at the top. So these are the steps you need to individually take to do blue, green, blue. On the bottom, it's the other color combination. So these are the steps you have to do to that. But we just match up on the right-hand side. Okay, so here's an epsilon 2 at the top. It goes to the first epsilon 2 on the bottom. Minimal step preserving path. Easiest thing you could think of. We've got two paths. One goes one way, one goes the other way. So you just match up the things. And this is what happens to this generator under this map. Any questions about that? Because I'm basically going to do the same thing a bunch of times now. So if that just went over everyone's heads, then I'm just going to continue to, no one's going to like this, but.
So just a quick question. Is it easy or hard to see that such a matchup on the right-hand side is unique? Is it possible that you could have like the same label with the same color, but maybe appearing twice at different spots that you can?
Well, so there's a 2 here, and so it's not about matching up the colors. It's just saying, okay, if this 2 happens first, it goes to the first 2. If this 2 happens second, it goes to the second time we see it too. And then I guess the thing that you're asking is it obvious that the colors match up? And it sort of is, because you can think of it as coming from if you think of it in terms of the partition where we're adding things, then when you add a box in that second column, the order that you add the boxes tells you the colors. So whenever the first 2 you add after this idempotent here, so the first 2 I add at the top and the first 2 that I add at the bottom are always going to be the color that happens after the last two I saw. So they're always going to match. And that's the sort of thing. So that the steps will match up. It's just, yep, that's obvious. And the colors, it comes from sort of the definition of the colors.
I see.
Okay, so here's another one. What am I doing now? Okay, so this is my sort of determinant thing. So here I've got blue empty. I want to switch to empty blue. Okay, blue empty, empty blue, blue empty, empty blue. And then, okay, the Zirkel people wouldn't normally bother drawing anything here. They just say, well, that's just a straight strand. But we need to sort of say, okay, well, we need a little extra here. So we have to sort of add an extra generator to the Zirkel world where it says, okay, blank space matters, which corresponds to these p-empty sets. And then what do I do? Well, I put the top path and the bottom path just match the paths, and then I just match them up. Okay. And so, for instance, we're now going to show how you can just keep on doing this in order to get everything you want. So the spect module is all paths that terminate at a certain point lambda. So what we're going to do is we're going to first inflate through a single hyperplane. And oh, okay, I'm not going to do a big one yet. These are the other Zirkel generators. And so now we're going to talk about actually reflecting and changing the endpoint of a path. So we're going to reflect through these hyperplanes. This is not a very good slide. Let's see how it works. So let's approach from above. So here we have a concatenation of two paths. The first one walks through the thing. The second one almost gets down to the bottom and then bounces up. So if you think of this in terms of, okay, so P alpha goes through, P alpha flat bounces back. So on the bottom of this Zirkel algebra, I draw two pinks, which is the number of pinks we use to get there. And on the top, I draw the minimal number of pinks I could need. So here in the KLR algebra side, I've drawn the pink algebra, the path P alpha, and then the path P alpha flat. Okay, so that is just along the bottom, I've just written this path like so. And now I said I was going to change the endpoint. That's not quite true. Let's see what happens. Cool. So what I want to change is I want to go from walking through and then bouncing. I want to map that to simply doing nothing and then walking through. So in the KLR algebra, I do nothing, 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 and walk through. So this is the map that I want to understand. So let's go back to our old path. Our old path walked through the hyperplane and then bounced back. So I've written down all those steps along the bottom. This new path, it just walks in a circle, which I haven't drawn because it would just look ugly, and then walks through the path. And then these two terminate at the same point, and we just match everything up. And this is a particular generator for the Zirkel algebra on the left-hand side, and it's our friend easy as you like on the right-hand side. Okay. So we just bounced up from above. We're now going to bounce from below. And we're going to do it from a bigger example just to see if we can really get what's going on. So here, let's do a path which goes up to this point here in this alcove, which is 3 away from the origin. And let's say, okay, I'm going to walk there, which is alpha, blue, beta, gamma, pink, blue, green. And then I'm just going to walk in a circle for a while. But actually, I want to inflate this. So I want to be able to add a pink strand. So in the Zirkel world here, I've added the beginnings of pink strand on top, but left it how it is at the bottom. So what I want to turn is these 3 p-empty sets walking in a circle. I want to turn it into going up to the wall and back again. And so I just walked up to the wall and back again. But notice I needed to use, in my KLR algebra side, I need to use 3 p-empty sets because that path has 9 steps. And then the path P alpha flat also has 9 steps. So I've just stuck in enough empty sets to get it how I like it. So what's on the bottom here? So it's the path empty. So it's 2, 1, 3, 2, 1, 3, 2, 1, 3. That's just going wee in a circle. On the top, it's 2, 1, 2, 1, 2, 1, 3, 3, 3. So that's 2, 1, 2, 1, 2, 1, 3, 3, 3, back to where I started. So I've swapped, and here's a KL, there's a Zergel picture on the left, and on the right, we just match everything up as easy as you can. Same old rule, minimal step preserving path, and the colors match from that definition. And so this is how you construct the bases of these algebras. So here is a path that takes you to this point here. And what I want to do is sort of inflate this path, make it bigger, and sort of think, okay, well, that's an element of the spec module. I want to increase n and see how it gets bigger. So I'm going to add a pink spot here on the right. And on the left, that means adding this path, which was just the path which told you how to do the KLR picture. I'm not going to draw the KLR picture because it gets too big. But this is how these elements sort of generate the algebra. You just do all these reflections each time. They get pretty ugly. But then, oh, isn't that a nice one? So we've got all the way now. And that's why I sort of skipped through the first one. So we've gone pink, blue, pink, blue, pink, blue. And here we've sort of at each point added a different color strand. And depending on which, if we reflected upwards or downwards, we've added this fork here, or a spot, fork, spot, fork. And then, oh, the last thing is to, oh, okay. So that was the guy where I did pink, blue, pink, and then went back to where I started. And now I'm going to sort of push this thing through to the left-hand side. And that's that first generator that we saw, which moves from one side to the other. And so this is how you construct bases of these algebras. You just keep on doing these generators. Okay. So that was how the bases and the generators match up. So I'm just going to do one relation that's a nice one. And then if people don't have any real questions, then you can ask me what the other relation is. So here's a relation. So in the Zergel world, they have two cyclotomic relations. And these are the first one says, if I draw any diagram that starts with the color green, say, but green was a wall of the dominant chamber, so walking out of green meant, I've gone into the parabolic, well, then that's 0. So never walk out of the dominant chamber. That's what the first one says. It says, always stay in that top third that we colored in. And the second one is something else. It's a barbell thing. It's a bit more hard, but I'm just going to show you the first one, the one on the left. So how does this work? So, and it's a bit different to what we used to do for symmetric groups of people, but, and here W is any word, any sort of sequence of colors. So if whatever you do, if you started by walking out of the dominant chamber, it's over. Okay, well, gamma is a wall of the dominant chamber. If and only if P gamma is non-standard. So what am I saying? I'm saying if this green wall is at the bottom and you go through it, then the path which goes through it isn't a standard tableau, right? You've gone to a composition, so it's no longer standard. Okay, so green is a wall of the thing if and only if P gamma is non-standard, if and only if the idempotent in the KLR algebra is 0. And this is just a result of Hugh and Mathis from the cellular algebras paper. There you go. It's just saying in Zergel world, you say, do not go into the parabolic. In the KLR world, you say, don't consider compositions, just see partitions. It's pretty nice. And so, oh, phew, I did do a picture. Look, so there's this green wall. There I am leaving. There's this tableau on the right that isn't a partition. Boom. Picture on the left, that corresponds to the Zergel world. Picture on the right, clearly that's not going to be something we want to consider in the symmetric group. Okay, and I'm going to finish there on this enigmatic picture so that you can ask me about it and it can seem natural. Okay, thanks.
Great, thank you everyone. Let's please thank our speaker. Fantastic. Does anyone have any questions?
Yeah, oh, sorry.
Oh, no, go. I was going to say that we do have a question in the chat, but.
Oh, right. Well, could I ask a question about, I didn't understand your relation C1.
Oh,
Yeah.
cool.
So the strands are labeled by.
So
and
because I'm looking at SL3, there's just 3 colors, right? Green, blue, and pink in the Zergel world. And so what C1 says is that if I draw any strand, if I draw any sequence of vertical strands, and I start with a color, green or blue, which means I'm leaving the dominant chamber, well then, if I start with a green or blue strand, it doesn't matter what I do next, it's already 0. Does that make sense? So what this O times means is you sort of concatenate horizontally. So if I draw any picture where the first strand is green, if the second strand is some idempotent for some other word in green, blue, pink, doesn't matter what that word W is. Any diagram which starts with a vertical green strand is 0, or a blue. So there's a green strand here, a blue strand, a green wall here, a blue wall there. If you go out of the walls, it's 0.
I see. So you've chosen one root. You've chosen all but one root to be called like finite. I guess you're choosing the finite guy inside the F.
Yeah, exactly. So because this is the symmetric group case, this is so this picture at the top goes off to infinity, but so it tiles a sixth of the plane because this is affine A2 with the parabolic finite A2. So 1/6 because the symmetric group on 3 letters has 6 elements. But you can do it for other parabolics as well, but this just gives you decomposition numbers of different cyclotomic Hecke algebras. The ones I talked about in this talk were just the ones which give you the symmetric group decomposition numbers.
Great, thank you. Does anyone have any other comments or questions for Chris?
Yeah, Chris, I didn't understand your last picture. Could you explain it, please?
That picture? Oh,
Yeah.
Thank you, Emily. That's such a natural question. Well done. Since you asked, I'll show you. So here on the left, we've got this sort of spot and a strand next to each other, and I put them on top of a fork. And so what we have to do, and I'll just sort of rush through this. Here's my fork, right? So on the far left, there's a fork, but I've sort of factorized it so through this sort of timeline where on the far left, it's the path P alpha flat. On the far right, it's do nothing and then go through the wall. And then this, we've sort of slowly merged it from one to the other. So here, everything goes up, then it just goes up 2 steps, then just 1 step, then 0 steps. So this is sort of a timeline for how to merge one of these into the other. So we can rewrite the fork guy simply as, okay, put these paths in verticals in these lines. Okay, that gets me from F0 to F1. That gets me from F1 to F2. That gets me from F2 to F3. So I've now factorized this fork generator, which was the path that took you from the top to the bottom into 3 steps. I then do the same for the spot generator. So here, the spot guy, well, he took you from just going around over and over to at the beginning. Eventually, it takes you to the thing on the right where you go all the way up to the wall and bounce back. And so, okay, I draw at the bottom, there's one of those paths, on the top there's the other. There's the middle guy, and then I've just factorized it into 2 steps. And what the hell, we said it was spot times strand, so let's add the strand in. So now when we do now that we've got the timeline for the generators, we're just going to think of this fork spot contraction relation as, okay, I need to reflect the fork through this spot hyperplane. So here I've drawn, and it's not very easy to see, but I've just reflected. So here it's now P alpha flat, P alpha. So here I've gone through, and I've just bounced half of the wall picture back through the wall. So I've taken the picture of a fork and reflected it through. So this is the timeline for the reflection. So there at the top is this new thing, the right-hand side of the relation, and here on the bottom is the fork. And they look very similar, right? One's just obtained from the other by reflection. And so we apply these timelines to prove the relation. And how does that work? So I'll show you on the next slide. So here I've got fork at the bottom, spot idempotent strand on the top, and I want to concatenate them and see what happens. So first things first, I'm just going to put them together and highlight the bit where they meet. And then I just, okay, use the KLR relation to undo that little crossing there. And then, move him away. And then I relabel the bottom of the path by this new relation, this new fork spot relation thing, like so. So it's no longer fork, it's the reflection of the fork. And then with that new labeling, that actually just works out nicely. And you just sort of step by step, get rid of these regions like so. Done. So that's why when I do, so I started with, so I finished with the idempotent, vertical strands, and I started with fork on the bottom, spot on the top, strand next to it. And that compares nicely to, oh gosh, there's so many things, this guy, so right, spot, strand, fork, straight line. And then that's the same thing as the diagram at the end. So it's spot, fork, tra-la-la-la-la. So that was the point, sorry. There was clearly not enough time to explain that. So maybe it wasn't the best question to plant in the audience.
Thank you, Chris. I will pause the recording now. So if anyone has any more questions to ask,